So, as I mentioned last week, this week's topic is going to start with infinite limits, or limits as you're approaching infinity, or limits that could be approaching infinity. We've done some of this already with our graph analysis, right? So I'm going to skip over some of the basics. What I mean is I'm going to skip over examples like this, right? Limit as x approaches 2 from the left of 1 over x minus 2, right? We did that. We really talked about that extensively when we did graphs of rational functions, and we saw that, that whole concept of figuring out if it's approaching infinity or negative infinity. And we also have done basic ones like this, okay? So again, I'm not going to do that. We talked about that when we did graphing rational functions. So I also talked about how to figure, another basic one, like if it was, we talked about basic ones like that when we looked at graphs, and how you just look at the degrees, and especially when you're approaching infinity, you think about what really matters in these problems, and what really matters is that if I look at this, when I'm plugging in massive numbers, adding or subtracting 1 don't matter. You just look at the highest power here, and when they reduce down, right, that reduces to 1. So it really doesn't matter if it's approaching infinity or negative infinity, it's going to be 1 no matter what. Now that could change, like there's some problems where it changes depending on which one it approaches. I'll give you an example of one that changes, right, and this is not a basic one, this is a brand new one. Let's see, limit is x approaching infinity of x e to the x. Okay, for ourselves, and this is a tricky one. Well, actually, not this one. This one is not tricky because that's approaching infinity, and that's approaching infinity for ourselves, and so that's going to be infinity as well. So that one's not so bad. And if we think about the graph of e to the x, the graph of e to the x, you may or may not remember, looks something like this. Okay, and if you're scaling it by x, that means these are going to be getting larger and larger, right? The multipliers get larger as you go out, so it's just going to get to infinity a lot quicker. Right? That's not a hard one. Here's a hard one, though. Okay, and if we look at this, we look at each individual piece and look at the limits of each one, right? This is approaching negative infinity. This is approaching it's e to the negative infinity. Oh, that means it flips to the denominator. So if we think about it, this is the same as that. Okay, notice I got rid of the negative in front of the infinity, and I made it a positive infinity to help me think about this. Okay, so I changed this sign because the x is just kind of negative x. But for this one, right, I brought the e to the x to the denominator. Okay, because this is going to have, when I'm approaching negative infinity, these are going to be negative values for the exponent, which is going to flip it to the denominator. So that's why these two are equivalent to each other. And if we look at that, we look at this and say, okay, right, this is going to be negative infinity, this is going to be e to the infinity. Now, which one grows faster? That's what we think about, like which one's trending faster. And when we did the same idea on this one, when we say, okay, if you have a higher exponent, it's going to get there faster, right? But for this one, e to the x grows faster than just a regular equation. So the denominator is going to be getting much bigger, right? Since the denominator is much bigger, this is going to be approaching 0 for ourselves. Okay, and man, that seems kind of weird. But if we look at it, actually, you can't really justify it with a graph. It's all about the growth of functions and kind of rewriting it in this way. So this is the first of what we're going to talk about in the videos, and that they get harder. Okay, here's another one that is a little bit harder. Let's say we have right. Let's see, so I'm just looking through my examples here, find a good one for us to look at. And okay, got that. Okay, so here would be one that's a little trickier. So we're approaching infinity, right? 2x plus 3. Okay, so let's think about this in the same concept of same context of what we did before. This is a rational function, so we just need to look at the graph when you think about the what really matters to this. And if I'm thinking about what really matters, and I know that the adding 1 and adding 3 aren't going to really matter when it comes to extremely large values of x. Okay, so that really, the end behavior model for this one is end behavior model is this right here. Okay. We could even say, right, I'm writing out end behavior model just to remind ourselves like of that terminology, so next year you remember when it's on an AP Cal. So we can remember that these two are equivalent to each other. Okay. If I look at the reduced version of this, okay, all that, we get that, and so we can see that the limit as x approaches infinity is just root 2 over 2 for this one. Okay, right? That's not the same as the actual value, but that's just saying what's happening there. So basically, I think about what really mattered. I reduced my radical for what I had left over, and I got root 2 over 2. So that's one that involves radical in one spot. What if we had a radical in 2 different spots or 3 different spots? Let's try this example. Let's see. So we're going to deal with the 7th root of x cubed plus the 5th root of x to the 8th minus x to the negative 2. All of that over the 5th root of x to the 6th plus 3 times the 4th root of x cubed plus 6. Okay? So let's think about what really matters. Again, it's a rational function. When you see a rational function, all that matters is where's the largest power. So if I look at the top here, this is x to the 3/7. This is x to the 8/5. This right here is, well, x to the negative 2. It's already written that way. So which of those is the largest power? Remember, the largest power eventually, as you get larger and larger values that are being plugged in, is going to take over. So really, this and this don't matter for ourselves. All that really matters is this term. So the end behavior model tells us that the end behavior model for this trend analysis tells us that x to the 8/5 is eventually going to take over for the numerators. This whole thing is going to eventually look a lot like that. Right? For this, the end behavior, which one of these is going to model what happens at the end behavior? Well, obviously not plus 6. Right? And then this is x to the 6/5, and this is x to the 3/4. And yeah, there's a 3 times in front, and I'll put that there. Right? But that's not really important yet. What's really important is that this degree is greater than this degree. So the end behavior is modeled by x to the 6/5. I could go ahead and try to reduce that if I wanted to. It's really not necessary. I can see that the degree of the numerator is greater than the degree of the denominator. So as I approach infinity, this is also going to be approaching infinity. Okay? For ourselves. For what it's worth, you may ask, what happens to the limit as x approaches negative infinity? You'll only be asked for these if the function, if it's not a domain restriction. And for this one, negative values would be a domain restriction because of this guy right here, right? So, the fact that this, when you cube it, it's still negative and take the 4th root, and that'd be impossible. That'd be your imaginary numbers, and we're not worried about limits of imaginary numbers. We're just dealing with real numbers here. Oh, excuse me. So that's what we have for that limit. Let's go to the next one. Okay, so there's plenty more with those fractions, and you just kind of look at what the highest degree is, and if there's negatives, you don't worry about the negatives, you just worry about that highest degree. Okay?